Good afternoon. My name is Gabriel Mateescu. I'm from Virginia Tech. I will talk today about Moab Node-sets and how to get very accurate scheduling with the Moab Node-sets facility. So first, what are we talking about? A node-set is an abstraction of a node properties. A node-set is defined using several Moab parameters. The first one is node-set attribute, which specifies the node attribute that you are interested in. And the second one is the node-set list, and the node-set list is a list of attributes. So here I show a very simple example where we define two attributes, E1 and E2. So for each node we define what attributes the node has. So here we have for node 1 we define feature is E1, for node 2 feature E1, and for node 9 let's say feature E2. So each node has a property. In this case a node has either property E1 or E2. And then we said how to actually select a node set. So we select a node set by a feature, and this feature we specify what the feature is with the node set list. So basically the second line there says we have a node set list that contains nodes that have the feature E1, and then the other node set list has the feature E2. So here actually we have two node sets, node set E1 and node set E2. So in this case E1 will be nodes 1 and 2, E2 will be only node number 9. What is the idea with the node sets? So first let's look at a few more parameters. For a node set we can define a policy, and the policy tells us how to actually select the nodes that will be used for a job. So the policy one-off means from these two sets that we have E1 and E2, select only one node set. So basically this means a job will only run in set E1 or in set E2, cannot span both sets. We have other policies which are first off or any off, and the name actually is very explicit. The other policy that you can define is actually whether this selection is mandatory or optional. So if it is mandatory, we said node set is optional, false. If it is optional, we set it to true. So here is an example of actually node sets in action. So the node sets can help us avoid very low level specification, which is basically a set of host names. And we can make a node to be part of multiple node sets by attaching to that node multiple features. And node sets can also be nested, and I will show you an example. So let's assume you have a machine that has two cabinets. Each cabinet has 4 enclosures, and each enclosure has 4 node boards. And we want to schedule jobs so that jobs go into one single cabinet, doesn't spread to cabinets, so that we don't go over the 10 gigabit switch that is attached to each cabinet. So basically this is a topology-aware scheduling. So this shows what we want to do. We have 2 cabinets. Each cabinet has 4 enclosures. Each enclosure has each enclosure has 8 nodes. So we want the job to be either in the left cabinet or in the right cabinet, but not to span both cabinets, so that we minimize networking latency. To do this, for each node, we define to which cabinet it belongs. So here actually node 1 belongs to cabinet 1, so we define the feature. Because we have 32 nodes in each cabinet, we have node 1, node 2, up to node 32, all of them will have the feature C1. Nodes from 32 to 64, which is the second cabinet, will have the feature C2. So now this is just labeling each node with its membership in cluster in the cabinet 1 or 2. And now we set the policy. We set the policy one-off, and one-off policy will apply to this node set list. And the node set list contains 2 sets, C1, which is cabinet 1, and C2, which is cabinet 2. So basically with this setup, a job will be scheduled either to cabinet 1 or 2. Cannot span more than one cabinet. So we get topology-aware scheduling. This is good, but it has a small problem. The small problem that it has is that actually if you have some room in cabinet 1 and some room in cabinet 2, we couldn't schedule a job to span both cabinets. So sometimes you want to actually fill in the holes. To fill in the holes, we use nested node sets. So with nested node sets, each node has more than one feature. So for example, node 1 has two features. C1, which is it belongs to cabinet 1, but it also has feature C1, 2, which basically means it belongs to both cabinet 1, to either cabinet 1 and cabinet 2. So basically, we add to all the nodes the feature C1, 2. And now, in the node set list, we put C1, C2, and then C1, 2. And we put the policy can be either one off or first off. So basically, this means the job will get into cabinet 1 if there is room there. The job will get otherwise in cabinet 2 if there is room there. But if there is just a little room in C1 and a little bit room in C2, and we can make the job fit in both cabinets, we also have C1, 2. So this is, we combine topology over scheduling with maximizing resource utilization. Well, so far so good, except that we may want to get even at finer grain. Finer grain will be actually to control location within a cabinet. So within a cabinet, you want to control location to have the nodes in the same enclosure. So we define yet another node feature, which is to each enclosure it belongs. So let's attach here labels to all the enclosures. So the first cabinet has 4 enclosures, the second 4, so you now have 8 more labels. And for each node, we attach a new label, which is the enclosure to which it belongs. So for example, the first 8 nodes here in cabinet 1 will have label E1. The next 8 nodes will have label E2, and so on. So now we have for each node, we actually have 3 features. In addition to C1 and C1, 2, we have the enclosure to which the node belongs. So now we can control scheduling by defining the following node sets. The first one is E1. The second is E2, which basically means put the job in the first enclosure, put it in the second, put it in the third, put it in the fourth, and so on. We list all the 8 enclosures. So this is like scheduling tight within an enclosure. But what if the job doesn't fit within an enclosure? Then you have C1, which is put it in the first cabinet. Then we have C2, which is put it in the second cabinet. And then we have C1, 2, put it anywhere in this cluster. So let me give an example with this node set definition. Let's assume we have 4 jobs. And here each job, I give it the size in nodes. So you have sizes 4, 5, 6, 7, and 10. And let's define the job fragmentation being the number of enclosures divided by the minimum number of enclosures. So these jobs, all of them except the last one, have the theoretical job fragmentation is 1 because all of them fit within one enclosure. The last one having 10 nodes need 2 enclosures. So they have fragmentation 1 and 2 the last one. But with the policy that I said here, this policy will try to put a job in an enclosure, and then when it is done with all the enclosures, we try to put it in a cabinet. With this policy that I just showed, the first job will go in E1, second job in E2, third job in E3, fourth job in E4. So we basically are using a new enclosure for each job. But when you get to the job with 10 nodes, there is no free enclosure where to put it. So the last job with 10 nodes, we spread it over 4 enclosures. So basically here the maximum job fragmentation that we reach with this policy that I showed before is 4, while the optimum was 2. So basically we are doing we are not doing optimally. So let's improve this. So advanced nested node sets. So the problem was we are trying to do the best scheduling for each enclosure, but not thinking ahead. So thinking ahead means don't go to the next enclosure as long as there is room in this enclosure. So to encode this, we attach to each node not only the enclosure to which it belongs, but also sets of enclosures to which it belongs. So for example here, the nodes in the first enclosure will have three attributes. The first one is they belong to the first enclosure. but they also belong to the set of E1 and E2, and the indicate is by E1, 2. They also belong to the set enclosure 1 and enclosure 3, and the indicate is by E1, 3. So basically, by doing this, and this is just the labeling, now the node set list will be in such an order so that after we try to put the node in the first or in the second enclosure, then we relax. Then we try to put the job in enclosure 1 or enclosure 2. Then we try enclosure 3. If it doesn't fit enclosure 3, we try 2 or 3, and so on. For the same workload as before, with this advanced node set configuration, so the first job will be like before in enclosure 1. The second job 5 will be in enclosure 2. But the third job with 6 nodes, because now we try to put it in E1, there is no room there. We try to put it in E2, there is no room there. But now we have the rule E1, 2. So actually we put a node with 6, the job with 6 nodes, we'll put it in E1 and E2. The one with 7, we'll put it in E3. The one with 10, we try to put it in E2, 3, and 4. So now we reach the maximum fragmentation of 3. Which is not optimal, but it's actually, for this workload, is actually the best we can do. So basically, the point here is by defining an appropriate set of nodes, list of node sets, we can get very close to optimal packing of the jobs in enclosures. So I'm done if you have questions. Thank you.